All right, so let's sort of get started. There's a bunch of stuff that's going on today, so hopefully everything works out. Thank you everyone for attending. Thank you everyone for attending. This is the first time I'm like sort of teaching dispatch of materials. So a lot of the words I'm going to string together is probably the first time I'm saying those words out loud. So thank you for bearing with me on that end. A few things and links. Hopefully you have all of the packages installed, and I will put that into the chat for everyone to see on the Zoom side. The main takeaway is the binder link, essentially because of how binder works and how everything needs to get compiled from source. The build time is 2 hours and still going, so not really that feasible. I'll try to essentially have it built earlier. I thought setting it off around noon would give it enough time, but it clearly hasn't finished yet. So if you are planning to follow along, if you run through the installation steps, it will definitely be faster than you trying to launch a binder instance. I sent everyone a link to the GitHub repository. So even if you were here for the part 1 workshop instance, the data sets were updated. And so if you can, click on the little code button, download zip, and extract it onto your computer. And this will have all of the data sets that we are going to be working with for the next 2 days. The other thing, if you were here for the part 1 set of workshops, that set was much more polished. This set right here is really trying to take in a lot of the feedback I got in pre and post workshop surveys and string something together. So it may be too fast. It might not be enough. We'll see. There is the post workshop surveys are going to remain the same, but you don't have to answer all of the questions, but use it as a way to like send me feedback, and that would work. All right, so we'll get started. If we open up the on the top right corner, the link that I sent you, if you extract it, does come down as a, there is an RStudio project in there. So if you want to follow along, please open up that RStudio project. The version that I'm going to be working with is going to be named a little bit differently, primarily so I can send all of the code up onto the internet, specifically on GitHub. And so I'm not clashing with some of the other work that I'm sort of putting together in the background. And we'll essentially start off from scratch. If you are coming in from the part 1 section, again, the data set folder is updated. So you, at the very minimum, like copy paste the data folder from before to now, and then we'll sort of just get started on this set of materials. And another caveat is if you are trying to go to the ds4biomed website within the next, especially within like the next 3 days, it's probably going to go offline fairly often. And it's mainly just me doing updates, and it needs to be in a state where like the book actually renders. So I'll try my best to do all of my work, and so it only updates like once in the middle of the night. But there is a chance that there's a high chance that it will not render, or you'll get a 404 error when you go on the actual website. All right, so we'll start off. So let me know if you are sort of trying to catch up with following along, but hopefully the links to the data and everything are available to you. All right, and one more thing. If you are going to like send out the workshop materials and stuff, if they do sign up for the, if they do register for the workshop, they'll be part of that email list. So I rerun the email list like every time I'm going to send out an email, just in case someone like registers, they get the follow-up email. So if you are trying to like, hey, like here's some set of materials, and you also want them to get the links when the videos are, the video is posted and all of that, just have them go through the registration link and I'll see their email and they'll also get that on that end. So in the top right corner of RStudio, we can click on the little plus button, go to new R script, and we will have a brand new R script available for us. A lot of this stuff is I'm going to assume a lot of the information from part 1 is sort of there. So if you have a question, do let me know, but there's going to be a balance between me covering stuff from part 1 and me trying to go through the materials that we have planned. All right, so because this is our first script, I'm going to name this 01, and I'll call this 30_day, because we are going to work on a mock set of data that is something that you might see when you, if you work in a hospital. All right, so we're going to start off by loading up tidyverse. And that's going to give us a lot of the functions that we need to read CSV files, right? And eventually we'll move beyond working with CSV files. But for now, just to get a hang of, or just to review a lot of the stuff we covered, we're going to load up tidyverse and use the read_CSV function to pass in a data set. The data set we're going to use is going to be under data. There is a folder called Cynthia, and then there is the encounters data set. And we're going to save that into a variable called encounters. And where is this data set coming from? This data set comes from a project that is funded, and I believe it's also maintained by MITRE, and it is called Cynthia. You can Google this actual phrase here, Cynthia, and what they have done is they have created a program and also published the data that generates fake patient data in a hospital. And there are data formats. You can see the format that we're using right now is CSV. But if you have a fire, or like an HL7 fire instance, they do have data that you can import directly from there. And I don't know how to set up one of those. So we're going to be working with the raw CSV side. But you'll see here, if you use the bottom right-hand corner, if you go to data and go into Cynthia, you'll see that this is a bunch of CSV files. The one that we are looking at right now is the encounters data set. And an encounter is essentially if a patient is going around and something essentially happens to them, or they see a clinician, or they have an encounter, there's a new row of data that appears. So we can click on any part that's not the blue arrow. You see here some of the columns, there's an ID column. And if we scroll to the right a little bit, there is a start and a stop time. So that ID refers to the encounter ID. There is a start and stop, like how long that encounter was. So an encounter could be you visited you went to go see a clinician, and this is the length of that visit. Then you see the patient ID. So instead of using social security numbers, many times you'll see this called as a medical record number or an MRN. And so this is the mock MRN number for this particular patient. The organization and provider, there's going to be information about like where this encounter happened, who's paying for it, what type of encounter was this. So you can see in that first row, this was an ambulatory visit. And there is codes essentially like an ICD-10 code around why did they show up, and then, cost of visit and stuff like that. And when I was putting together this data set, one of the things that was sort of like amusing was for $130, you can have a hospital encounter for acute bronchitis. And apparently that's very cheap, especially as a claim, like not even like out of pocket cost. So you're going to see this 129 number a lot. And again, that's just one of the things that I discovered, that, yeah, this is generated data. So a lot of the costs of things are not going to be realistic. Other things in the Cynthia data set, and you can feel free to use this and explore on your own. There's also a patient's data set that we'll look at later on. And when we talked about tidy data in part one of the things in the tidy data paper was that point 3 that we didn't talk about in tidy data, which was data normalization, which is really the process of splitting out a data set into all of these separate individual tables. And the way you do that is using the filter commands that we covered to subset your data and then write it out as the CSV to make sure that each data set really is just like measuring one thing. So that's a little bit about the encounters data set. We'll start off with a little exercise. Hopefully people can see this, but looking at the encounters data set, I want you to put out the code that will calculate how many encounters were there for each unique value of description. And I also want you to, there's another column in there called reason description, and try to write out the code to get you how many encounters there were for a unique value of reason description. And then do the same thing, but look at it from, is there a combination between description and reason description? And so this is going to, we'll take about a minute to work on this bit and treat this as like, hey, this is hospital data. Why did I call this file 30-day? It's because we're going to try to answer the question around how many patients in here came into the hospital with a heart attack, and how many of those people who came into the hospital with a heart attack came back within 30 days. So that is a pretty common question that a lot of hospitals ask, especially in the United States, because that's how billing works. Well, insurance reimbursements work. So we're going to slowly work on that problem. And the first thing we need to know is trying to figure out what's in here. So we'll take a couple of minutes. We'll take about a minute to sort of go through these questions and also treat it as a way for people to catch up. All right, let's go through this question or this series of questions. So the first question asked about looking at the description column in the encounters data set. How many encounters were there for each unique value of description? So we can say the encounters data set. The trick here is knowing that this is a group by operation. And for each unique value of description, we're going to put in description. And then we're going to pipe that into trying to get a count of something. There's multiple ways if you're familiar with tidyverse stuff, but the way I showed you in part 1 was using the summarize and then calling count is the number of rows in that group. And then what I also did as part of the scaffolding code is reverse sorting by the count. And you can see here that about almost 15,000 of these values are going to be a general examination, and there's other different types of encounters as defined in the description column. The next part of the question was really the same thing, but we're trying to figure out, well, there were 2 columns that refer to what type of visit this was, or why did they show up here. So the trick really was to really run the same code again and look at the reason. So you can see here, there's going to be a lot of NA values. So we kind of need to figure out why is there an NA value, but maybe like the description, clearly not every single description has a reason for it, right? And we might be able to figure out like some patterns involved in that case. And then the last question was really, hey, we're going to run the same thing. We have those 2 data sets. Let's do essentially like a crosstab between all of them. And you can see like, yeah, a lot of it's going to be general examinations. It's just a general reason. There's no actual reason. They just showed up for a general examination. And then something that does look like that has a reason is going to be a lot of these visits are going to be probably in OB or something like that. And then we have a few urgent care visits, et cetera, et cetera. So that's a little bit about this particular data set. And if we want to get just a list of columns, whoops, in a data set, we can run the function names around the column, around the data set, and you'll see we get a bunch of the column names in our data set. And so one of the things, since we're talking about part 2 things, and this is something that's going to be a little bit new, is remember when I talked about having a good column name, and part of the definition of a good column name is, use underscores, don't use spaces, don't begin with a number. So that's why a lot of data sets, like instead of like 0 or 1, 2, 3 to 31 for day of the month, like it'll be like M1 or D1, D2, right? And it's because computers don't really like things beginning with a number. And so there's going to be a lot of issues, especially if you're self-curating a data set like that. And so I'd like to bring you to a package called Janitor. I guess I don't have this installed. That's going to be interesting. So if you don't have this installed, you can click on the packages panel here and install Janitor. I don't know why I don't have it installed. It probably is, it's definitely installed somewhere on my computer. But anyway, there's a package called Janitor. Janitor is a very useful package. There's a lot of very common data cleaning steps that is in the Janitor package, and I highly suggest you look into it if you haven't. But really, one of the most common and more useful steps, functions in the Janitor package is there's a function called clean_names. And if we give that a data frame, it's going to clean the column names in our data frame. So we will need to reassign this data set. And if we look at the column names here after passing it around clean names, you'll see that it'll clean the column names of your data. So one thing turns everything lowercase, gets rid of spaces, puts underscores instead of periods. If column names like begin and end with like white space, like because someone decided to put spaces to center something in Excel, it'll try its best to fix that. And if you're working with data set where you don't know where the source is, I would highly encourage you to use the clean names function. And that way you don't have to worry about how the casing is on all your data sets. So you notice that from some of the data sets from part one was there were mixed cases. Like when I created a new column, it was all lowercase with underscores, but some of the data that I loaded in had like, it started off with a capital letter, et cetera, et cetera. And so this way it just turns everything lowercase and it reduces the amount of potential spelling mistakes that you would have. All right, so we're gonna talk about this encounters data set. And so let's subset some of the columns that we need, right? We don't, if our question right now is, let's figure out which are the patients that have come back into the emergency room within 30 days, we don't need a lot of this information, right? So for a particular question, we don't really need, for example, the payers column or the payers coverage. What are the things that we care about right now for the question of interest? We can use the select function within tidyverse. And now we can say, I want the ID column, because every time you select something, always make sure you keep an ID column with it. So we have ID, we want the start and stop, because we also want to see like if they do come into the ED, we need the start and stop date because we need to know when they came in and when they left and if they came back again. So we do need like the time for the encounter. We're trying to figure out who these patients are. So we're gonna want the patient. And then the encounter class tells us if it was ambulatory, if it was a emergency visit, et cetera, et cetera. So we do also want that information. And then description and reason description. And so we can use the select function to, again, pull out only the columns we need. One, hopefully it'll fit better on your screen. Two, if there are a lot of columns, it'll help you go through the data without having to scroll to find the columns that you want, right? Only keep really what you need. And if you need more columns, well, it's really as simple as put that column that you want like at the very top. So this is nice. You'll notice that like I typed a lot and I had to type each individual one. And as another review, we don't have to type every single column. In tidyverse, for example, if I want all of the columns from ID to patient, because the original data set like had those all in sequence, well, we can say like, hey, I want these ranges of columns. So we can put a single colon there. So I want all of the columns between ID and patient. And then there's some columns I didn't care about. The next one was encounter class. Then the next one was description and reason description. And you can see here that one really just saves us a lot of typing. Two, for example, if you do end up working with survey data, you can say like from Q1 to like Q1A to Q1Z, and you don't have to type every single one. So there's a lot of helper ways for us to select data. So let's say this is the data set we want to work with. So let's save this into encounters, column, sub, and let's save that to a variable. And now you'll see that instead of looking at 15 variables, we're really just focusing on the 7 variables that will help us answer our question. All right, so let's take about like a minute or so. And the question that we have here is 30-day readmittance for a heart attack. We know that it has something to do with description and reason description to look for heart attack. So take a couple of seconds. What you can do is, and this is literally what I did when I was exploring, was I opened this and you'll notice that you can click on filter and you can like filter on text, Or you can use this global filter over here just to see what's going on. You might use like unique values. You might tabulate using group bind, summarize, and tabulate. Use all of those methods to figure out how is heart attack encoded in this data set. All right, cool. So it took me a bunch of time trying to solve this question, but actually, if you go through this data set, heart attack is encoded two ways. And they're both encoded in the description column. They're encoded as either a cardiac arrest or a myocardial infarction. There are subtle differences between them. You can have a cardiac arrest for other reasons other than a myocardial infarction. So there is a sort of like a set issue with our data. But those are going to be the two terms that we're going to use to define heart attack in our data. So we want to then be able to filter this data set, this encounters data set, for just the encounters that are heart attack related. So how do we do that? Well, we can take our encounters column sub. And so instead of selecting columns, we're filtering on rows. And the way we're filtering this is looking at the description column. And if it's equal to cardiac arrest with capitalization, or so using that pipe operator for or, we're not using a comma for and because a description value can't be both. It's literally just one. So it's either a cardiac arrest or the description is equal to myocardial infarction. And so we can run that bit of code and we can see that like it's now filtered this data set from 53,000 encounters to 70. So there's 70 encounters in this particular hospital that had a heart attack. And how did I know that it's in a particular hospital? Well, it's because I did a little bit of the data exploration on our side, on my side. And this is really like, I thought this would be like around the United States, but it's really like all in Massachusetts. It's really where everything is. So one question was, could I wildcard my search? You can. We'll talk a little bit about string methods, but you can use like different like coding, like wildcards, like a star for like a whole bunch of things afterwards. You totally can. We'll cover a little bit about string methods in a little bit, and we'll incorporate those as we go on. So the other thing about the part 2 lesson is because it's less completely from scratch, a lot of the examples that we're going through is like, we'll work through a problem, and in working through that problem, there's going to be a lot of things that I'll try to teach you. So instead of teaching one concept at a time, it's going to be multiple concepts at a time, but it's all in the context of working through a particular problem. So we have these two terms, cardiac arrest, myocardial infarction. There might be a situation where like, hey, maybe we're trying to look for more than just these two terms for 30-day readmittance. And so we want to make it a little bit easier for ourselves instead of like, putting vertical pipes over and over again. So let's save this to a term called MI terms, and it'll stand for myocardial infarction terms. So AMI, acute myocardial infarction, is like the other term that you use for heart attack. And so in here, we can say cardiac arrest, comma, myocardial infarction. And so this way, we're using the C function to concatenate, like create a list of things. It's not technically a list, but it's a list of things. And this way, if we need to add more terms, all we need to do is say comma and just keep adding terms as needed. So it'll save us a lot of typing. One other thing, and I talked about using the janitor package to make sure like the spelling is consistent, like especially the casing is consistent. And so the first little string method I want to show you is we can take this set of characters, and within tidyverse, there's a whole slew of functions that begin with str underscore. That stands for string. So if you're trying to find like, hey, I'm working with text data, like what can I do with it? So str underscore helps you find all of the things that you can do with strings, and you'll see that it's like coming from the string R package. It automatically gets loaded up with tidyverse, so you don't have to be explicit. There's a really handy function called string to lower. And what that does is turns everything lowercase. So you really don't have to worry about like, is cardiac arrest capital C, lowercase a, all capital, all lowercase? It doesn't matter. You can now copy and paste terms wherever you get it from the internet, and then just know that if you're going to do comparisons, you as the programmer, all you have to worry about is everything is in lowercase. So that's really useful because we can then rewrite the encounters data, this filtering step. We can use the filtering step, and instead of having to write description equal, et cetera, we can also say like, hey, I want to do all of these string comparisons. I want to compare them such that use them as the lowercase version of that column. So we can actually pass in string to lower around the description column, right? And that'll automatically turn everything lowercase. And because we're comparing one group and seeing if the MI terms is contained in that column, we can use % in % and then MI terms. And what this will do is, if the value of description in its lowercase form is in this list of values called MI terms, then that's how I want you to filter your data set. And this makes your data a little bit more readable. If you need to make modifications, you can. And you can look into, instead of string to lower, there's another one called like string detect. So you can see if it detects a pattern. And so that's where you can start using wildcards and stuff like that. So that's all going to be handled within string R. And that's one of the string examples that we'll use. And so I don't want to end up sort of beating the point where like I talk to you about every single possible string function, but this is where you go look for that. All right, so we filtered our data set. So let's save this into a variable called MI encounters. These are just our myocardial infarction encounters. You'll see here, it is now just 22 observations across 7 variables. These are encounters. So even though if we look at the ID, remember the ID, these are 22 encounters. We don't know if a patient came in here twice, right? So I kind of know if you click the little sort, like some of these values might show up twice, and that's because that's the same patient. So, you know, looking at it, just eyeballing it, we know at least a patient came in here multiple times, and we want to figure out where those patients are. So let's actually do the analysis, right? Because just eyeballing it isn't enough for you to write a report. So let's write the code to give us the actual count. We have MI encounters. And I can show you the example that we did in the beginning, which was group by and then sum and summarize and using the end function. But actually, there's another shortcut for it. And we can simply say count and then give me the count of the patient. right? So each patient, the patient column is a patient ID. So I really just want the count of the patient columns to see how many patients came up twice. I want to reverse sort it. So the patients that came up multiple times showed up here. I believe I spelled something wrong. So give me once. Yeah, cardiac arrest. So yeah, so I made a spelling error here. Nothing you can do wrong. Nothing you can do about spelling errors, but at least the case, since the case is something you don't have to worry too much about. So what you should be left with is a data set that is hopefully 66 rows and 2 columns. And you can see here, these are the patients I care about, right? Because what is the question that we're trying to answer? Did they come back with a heart attack within 30 days? And how do we know if they came back within 30 days? Well, they first have to come into the hospital twice. So these are the values or the patients that I'm going to care about. So let's just pull out these patient IDs, right? Because then we can use these patient IDs to just filter the encounters data set. And then we get the encounters for all of those patients. So the patient of interest. So what's the next bit? So let's go and pull out these patient values. So given this data set, I can then say filter where n, this column n, is greater than 1. And you can see I got all of this data set of frequency counts. That's just the patients that showed up more than once. And so now I'm going to use something very similar to that percent in percent that we just did. But the first thing I need to do is I need these actual patient IDs. And so I'm going to pass this into a function called pull out the patient column. If I look at that, it's now just a quote unquote list of patient IDs. So that's really great because now I can save that patient MI repeat IDs. So now I just have the patient IDs and then go back into that filtering step that I showed you before and filter the patients such that our data set is just a patient of interest. So where is that data set coming from? Well, that's the encounters call subset. We're going to filter this data set such that the patient column is in one of one of these values is in the patient's column. So if we run that, if we run that block, we'll see that, well, if we just filter this data set with those patients, there's 202 rows. So we had those 4 patients, they came into the hospital with at least once for cardiac arrest, but they've had in total with all of those 4 patients, 202 encounters. Well, that makes sense because in the hospital system, you came to see a clinician for other reasons, including heart attacks. All right, so let's save this to a data set, or yeah, let's save this to patient encounter MI. So these are the patients that had an MI encounter. And let's use that arrange function again to just sort the data set. So it's a little bit more useful for us to visually spot check. And if you want to save it out, it's also easier for the people down the line if they're trying to visually spot check. So I first want to sort on patient just so the patients are all like together and grouped together. And then I want to sort by the start time. And then if they have similar start times, like sort by a stop time. All right, so now if we look at this data set, patient encounter MI, what's going on here? So you can see here, this particular patient came to the hospital a bunch of times, right? So like I said, like these are also, if we scroll down to the right, they're coming in for ambulatory reasons. They come in for a couple of emergency reasons or inpatient reasons. They come to the hospital for many reasons. And we can see a lot of these times, they're all within the same day, right? So it doesn't, or like in this particular case, it's 24 hours. So that probably is an inpatient stay. And if we look to the right, it looks like it's an inpatient stay. If we scroll through description and reason description, we can see like, hey, this particular patient came in for acute bronchitis. We can scroll down and get a general history of this patient. And when we get to the part of like, well, we know this patient eventually came in with a heart attack. We can eventually see it. Yes, so they came in eventually for a heart attack, and then they came in for a heart attack again, but that second time was for a drug overdose, right? So we can get a sense of a person's history just by this data, just eyeballing it. And then if we want, we can see like, okay, so this is when they left the hospital the first time, and this is when they came back to the hospital the second time. And so just eyeballing it, they didn't come back within 30 days. So the hospital gets their reimbursement. But, you know, we can get a bleak view of the history of this patient. All right. So what was our question? 30-day readmittance. So now we want to filter. We see that they came in for a whole bunch of other reasons. So now we only care about the heart attacks. So how do we go about figuring that part out? Well, there's a few ways that we can do this, right? One way is if we look at this data set, you'll see that like, hey, one way we can do this is literally like filter by encounter class, right? That looks like a pretty decent way. So let's see what possible values of encounter class are there. So what possible values? So we have our patient encounter MI. And in tidyverse, there's actually a function called distinct. And if we give it a column, so encounter class, here are all the distinct values. And this is nice because you can see, hey, if they came in for a heart attack, it's probably an emergency. Maybe it's urgent care, but most likely an emergency. And you don't come into the hospital with a heart attack for ambulatory reasons, right? You're by definition not ambulatory. So, all right, so let's filter our data set using this form of our data. So we're going to use filter again. So we're going to say filter. And we can say, I want to filter where encounter class is in some set of values. So emergency or urgent care. And so we get this data set, it's got 19 values. So if we look at this, give me 1 second. So let's save this patient encounter MI like emergency. I spelled this wrong. It'll be okay. All right, let's look at this. So it's got 19 values. If we look at this data set, well, if we do that, not every single emergency is a heart attack. So they come in for urgent care. So clearly urgent care isn't the reason, but you know, they're not coming in for you know, a heart attack that is like at the fault of the hospital, right? Like if you come in for a heart attack for a drug overdose, that's a little bit different. So maybe we didn't specify this filtering correctly, right? So now if we're trying to do 30-day readmittance, if we're putting in and this data set is filtering on the wrong variable, well, you're going to be reporting like, hey, we actually should be reimbursed. And then the insurance company is going to fight you and be like, no, you're not. So you might have to think about how are you filtering your data? Just because you see one way and your code works doesn't mean it's the correct solution. So how do we go and figure out like, okay, no, I actually care about like the cardiac arrest cases. So remember, we have that MI terms data set. So actually, let's go and use that because we created it before. Let's use that to filter. So what I really want is patient encounter MI only. And it's going to go off of patient encounter MI. And we're going to filter. And we're going to filter the columns. They're all lower again. So str to lower of description. Is it in the MI terms list? And you can see this is really useful because now all I need to do is change my code in one location and this whole report or this whole batch of code updates. So if I look at this data set, encounter only, we have 8 rows. This particular, we can see all of these are going to be cardiac arrest or heart attack cases. And all we know, these are patients that came into the hospital more than once. So each one of these patients, and in this particular case, comes in pairs. So we can eyeball the stop date of the first thing and compare it to the start date of the next. And we can eyeball the 30-day calculation there. And you can see here, like, hey, that actually seems pretty good for this hospital. No one's coming back for within 30 days, right? But we don't know that for sure. So we can't really stop there. And so we really also want to write the code so we do that, like make the actual calculation. What does that involve? Well, that involves working with dates. And dates are going to be painful regardless. It's painful. It's so painful. So one thing that you have to understand about how computers report dates is most computers and most programs they keep track of the date by having a second tick from a starting point. And that reference point is January 1st, 1970. It is the start of the Unix operating system for most computers and operating systems. That is the birth of computers, January 1st, 1970. So the date is always calculated by seconds from January 1st, 1970. And then all of the date arithmetic is relative to that. And that's why a couple of years ago, there was a whole big thing in the computing world because 1 billion seconds is about 33 years. And And so, there was the billionth second of computer's existence celebration a couple of years ago, or somewhat recently. Except, I keep making this exception, except in Excel. The birth date for how time is calculated is different in Excel. And that birth date is like January 1st, 1990 or 1900. It's like one of those, and it's completely different. And so you have to be careful when you get the set value of a date in Excel. That's why sometimes when you export dates out of Excel, it's just like this, not a date number. That's why. And it's so insidious and to the point where like actually in the janitor function, there's literally a function called like fix Excel dates, and it will fix the date problem. So if you ever load up dates into R, or in this particular case R, and the date's off, it's literally because it's probably got exported out of Excel and there's a function for that. So I'll point you to that. But we're gonna work with dates. The way we work with dates in a more easy example is using a function or a package called lubridate. The today, just so you have a reference, is when this data set was created, 28. So this is when the Cynthia data set was created. So if we have a string that's this thing, year, month, day, there's literally a function in lubridate that says like, give me the year, treat this string as a year, month, day string. And now you get an actual timestamp. So you can actually do like date arithmetic with these things. So we're going to utilize this behavior to, one, this is going to be a little bit extra because our columns are already loaded in as date timestamps, but I want to show you how you can convert string columns into date timestamps. So we are going to take this patient encounter MI only. And how do we create or modify existing columns? Part of this is also a little bit of review. There's a tidyverse function called mutate. And then we can say stop date time is going to be, so if we look at our column here, this is actually represented as a year, month, day underscore hour, minute, seconds. And there's a function in looper date that interprets a string as year, month, day, hour, minute, seconds, and it tries its best to give you the conversion for it. And so the stop date will pass in the stop column. And then the start DT is going to be hour, minute, seconds of the start column. And I sort of like, did I not load this? Year, month, day, hour, minute, seconds. So if I type it correctly. So that'll give us two columns, one called stop DT and start DT, and I'll read in that as a column. So that's something that you would do. In this case, it's a little bit extra, but now that you've converted it into a proper date timestamp, you can use the select function to drop the original column. So you don't want to accidentally call the wrong column. So we'll drop using the negative sign, drop the start column, drop the stop column. Cool. So now we just have a 8 row, 7 column data set. And so now we can do date arithmetic. So we can now say mutate, and let's just see how long these visits were, right? Just to show you that you can do date arithmetic. So for a given row, because we have start time and stop time, we can calculate the difference. So how long was each visit? So in general, it's final minus initial. So it's stop DT minus start DT. And if we save this back to the data set, and we look at our encounters MI only data set, if we scroll to the right, you see we now have encounter lengths. And you can see all of these ED visits was an hour and 1.3 long, right? That's pretty impressive as far as heart attack encounters go. But again, this is also made up data. So, you know, we can maybe do this in your clinic. You might like, instead of just looking at heart attacks, and if you have your own clinic or your own private practice, maybe you want to get a sense of like how long your patient visits are, right? So when did they check in, and when did maybe not like when the clinician finished their note, but you might have a marker of like something else. And you can compare and see like average patients are coming in and staying for this long. And you can do something similar if you're trying to calculate like wait times or something. All right, so now our question is, all right, we're able to do date time math. But the problem right now is we actually want the start value of the next observation in the row that we're currently in. So then we can do the date calculation, right? We need to capture information from the next row. And so another thing that you can do is you can actually pick another column and then shift it up and down by a certain amount. That's called leading a column or lagging a column. So what we want to do is, what do we want to do? We want to do final minus initial. So stop minus start, but we want the start to be the start value of the next observation. So what we need to do is take the start column and shift it up one, right? Because we've sorted our data set on patient. And if we stored it also on start, we can like use that sorting operation and then shift a column. So we can do this in R as well. So given this particular data set, we can mutate. So we're going to make a modification to this data set, and we're going to say next encounter start is equal to, we're going to lead a column start DT. And if we look at that, you'll notice that, let me save this. if we look at this, you'll see that we created another column called next encounter start. This value is the start DT just shifted up 1, right? And now if we look at a particular row, all we need to do is subtract stop time and start time to get whether or not they came back within 30 days, right? So now that we have that column mutation, we can say like the next encounter length, well, we really just take that column we just created, subtract it from the start DT. And if I save this into a variable, or if I look at this, you'll notice that like, okay, for patient 1, their next ED visit was 300 days, but then you get something really weird. Like you get these massive numbers. And that's because all we did was blindly shift the columns up. And so like, why is this negative 2000 here? Well, that's because this 1955 date that we used the lead for is from the next patient. Like that's just incorrect, right? Like why are we running a calculation from the next patient? So we need to fix a little bit of this code that we just wrote, because we can't just blindly pick a column and lead or lag those set of results. So what's the thing that we actually want? Well, the process is correct, right? We still want to do a lead, but instead of just leading the column blindly, we actually want to break up that calculation for each individual patient. So one patient's values doesn't bleed into the other. And so how do we break up calculations? Well, that's where group by comes in again, because we can group by patient, perform this operation, and then stack the data set back together. All right, so how do we do that? We're still working with this patient MI only. So that's the version I saved that has the encounter length. So we're going to work with that. We're now going to say group by patient, and then run the same thing again. So this mutate column that we just wrote, we can copy paste that. And now if I look at this, 1, you'll get missing values, and that makes sense because that particular patient doesn't have another another encounter in the ED, so that's fine. And now we can see, okay, this patient came into ED, first time between events was 301 days. We have another patient came in about 10,000 days later, 2,000 days, 2,000 days, et cetera, et cetera. So that's what we want, right? We now can very quickly see, like, of all the patients that came into the emergency room more than once, how much time was there. One thing you want to notice, if you look at this data set, because we ran group by and then did mutate, the data set is not actually what you think it is. And in the grouping printout, it says any other calculation you do is going to automatically be done by the grouped by patient, right? So that's something you want to be very careful of. And that's something that people do not pay attention to. And I'm telling you right now, anytime you type the words group by, immediately follow by the term ungroup, run your calculation, and then do it. And now you see you're back with a regular flat data frame, and you don't have to worry about your calculations always being done by a patient. And this is a problem that you will see in Twitter, like every other week, someone gets bitten by this. And that means like calculations later on it will affect your calculations later on. So we have this. So now let's save this, mi_re-encounter. So I'm going to save this. This is a data set that sort of makes sense. And we eyeballed it. None of our patients have 30-day readmittance, but let's write the actual code, right? Because this might show up in a report. So let's filter where next encounter Was it start or stop? What did I call it? Length. Next encounter length is less than 30. Like, did they come back within 30 days? We get a data set with 0 observations. All right, so what happens if we want to do something else, like 365.25? Are there patients that came back for a heart attack within 5 years? Yes, there's this one patient that came back with a heart attack within 5 years. And now we can say, like, okay, what about patients? Did anyone come into the ED within 10 years? And you'll notice that, yes, there's 3 patients in the data set that came back within 10 years for a heart attack. All right, so hopefully that was a review and also a couple of new stuff all wrapped up together in one block. Let's take a 5-minute break and we'll play a little bit more with the mock data set that we have here and we'll try to incorporate, like, what is the question that we want to ask here? Like, we have these patients that came into the hospital for a heart attack. Like, what if we want to see, like, how old were they? Like, right now, we don't have any information in the encounters data set telling us how old they were. Where do we find that? Well, there's this patient data set that gives us the patient's age or birthday. So with that, we can tack on more information, and how do we work with multiple data sets at once is the next thing I'm going to cover. So we'll come back at 10 past the hour, and hopefully you're relatively caught up. But if you have any questions, just let me know, and I will try to keep up with literally the 3 communication streams that I have in front of me. so let's talk about our next topic. And like I mentioned, we can so hopefully you can see the screen at this point. If I make it any bigger, you're not going to be able to see other things. So, all right, we'll make another R script. And I'm going to save this and I'm going to call this 02 and I'll call this joins. And so now we're going to go through the process of working with multiple data sets. This is a brand new R instance. So what I'm going to do is I'm going to restart the session just to make sure everything I worked on before is not showing up. So we start off with a nice clean slate. And I'm now going to library tidyverse again. And then library janitor. So I'm going to load up those two libraries. And we're going to go through we're going to work with the encounters data set again. So I'm going to read our CSV file. It's going to be under data, Cynthia, and then encounters. Oops, it's not care plans. So we have our encounters data set, and you'll notice that it will load up data set with this mixed capitalization, especially this ID. So I'm going to pass this into clean_names. And so now when I look at the encounters data set, the columns are all in a standardized format. All right, so let's review a little of the things that we left off with. So let's see, remember we were just looking at values where the encounter was a cardiac arrest or a myocardial infarction. So we'll make a data set again, encounters_MI. The question is, how do you restart the session? The keyboard shortcut on Windows is Control-Shift-F10. But the button clicking is on the top, you'll see session, and then you can click on Restart R, and then it'll tell you what the actual keyboard shortcut is. And restarting the session really, especially if you're working with different files and you're trying to create pipelines, is a really good way to make sure that that particular script is self-contained. You're not relying on some other code to be executed before this one. So we're going to run the encounters data set, and then we're going to say, we're going to filter. And what are we going to filter? We're going to filter such that the lowercase value of description is in, and then I can say the lowercase value new line. The lowercase value of cardiac arrest and myocardial infarction. And why did I wrap around string to lower? Again, it's so like I'm making everything consistent. If I end up copying pasting values, I don't have to worry too much about how they're being copy and pasted, et cetera, et cetera. Especially like maybe it's okay because this is coming out of a health database and this stuff is ICD-10 coming from ICD-10 codes, and that's probably going to have a consistent spelling or capitalization. Again, you never know, and I almost never trust that. So if you're going to make character comparisons, one, make sure it's spelled correctly, like again, I like messed that part up. And then 2, just turn everything lowercase, and then your life will be much, much happier. So this encounters data set has 70 rows and 15 columns. You'll see that in the top right-hand corner. My screen is too blown up to show that, but that's what you should end up with. So what is the question? The question that we want to answer now is, how old was the patient at the time of the heart attack? So the question was, can I use the same clean function for these names? I don't think so. So clean names takes a data set as input and gives you a data set as output. String to lower does not take a data set as input. It takes a vector or like a list of values. So that's where these two functions are a little bit different. The input and the output of these functions are different. And so that's why they're different functions. So if you ever, so clean names is literally a quick command for like, just clean up all of the columns in my data set. The column names. Versus like, turn everything into lowercase. This only does everything into lowercase. It's not actually doing clean names. So this, all it does is lowercase. So if you put in a whole bunch of spaces here, it's not going to fix that. So there's another function called str, I think, trim, that will trim the beginning and end. And if it has white space, it'll get rid of it. So if you're working with individual strings, str underscore, look for all of those functions. And if you need the computer to do something like those operations, chances are it already exists. Like if you want to find stuff, clean stuff, like chances are it exists. You just have to like go and look for it and piece together the bits that you need. But a lot of those fundamental things already exist, and someone has already built that for you. Okay, so the question is, how old was the patient at the time of heart attack? Well, if we look at the encounters data set, there's no way we can answer that question. We have length of the encounter, and we have a patient, but nowhere in here we can calculate age of the patient. And that's because this is only a data set about encounters. So if we can, there's a data set called patients. So we can load up the patients data set. We're going to load up this data set exactly the same way. We're going to use read CSV. It's going to be under data. For me, it's like we put it under Cynthia, patients.csv. And then I'm also then going to pass it into clean underscore names. And now we have a patient's data set. If we look at this data set, we have ID. So this is now the patient ID. That is different from the encounter ID, but it is the same value as the patient column in the encounters data set. So you can see like these data sets have what are known as keys that you can use to match things on. And when you're putting together data sets or when you're working with databases, knowing what the key is for a particular data set or table is really important. And that's why I say, like, even if you are selecting columns, almost never drop the column that is the key. Even if you never end up using it, make sure your data set always travels with some kind of identifier. Maybe you have to make up your own. Maybe it's not feasible because the patient MRN number is like HIPAA and you can't just publish that. So in that case, make up another key and then somewhere you keep track of how those are being related, because otherwise you're never going to be able to answer this question of how old was my patient at the time of heart attack. And yes, one of the comments was, yes, that's how relational data sets work or relational databases work. So we have our patient's data set. In the patient's data set, if I go back again, it's literally a column called birth date. So now we can actually calculate how old they were. How do we calculate that? Well, we take today's time, and remember today is like the August 2020 because that's the age of the data set. So today's time is their age, but that's their age today. We want to take their birthday and subtract it from the time of the starting encounter. That is the time of, that is their age at that encounter. But we can do all of that with birth date. Okay, so now we need to go and combine these two tables. I sort of cheated, mainly because I am not going to recreate things that that work. And so this is coming straight out of the R4DS book, how table joins work. There's multiple types of joins. There's one called inner join that says if you have a left table and a right table, we base on the key. So that's the ID column in the encounters data set and the ID column in the patient's data set. Sorry, the patient's column in the encounters data set matched with the ID column in the patient's data set. Those are the two joining values. And if we find a match, we only return the values that matched. That is an inner join. We can do all sorts of types of joins. We can say, keep every single value on the left-hand side and only match in the results from the right. So that way we're always having left-hand values. Or we can do it the other way, only keep the right-hand values. Or keep both of them. And if there's missing values, just leave them as missing, right? So there's Venn diagrams. You'll see this a lot when you're working with relational data. You can do all of that in R. The main point is you have a column that you can use to match on. So let's go and do this in R. We have those two columns. We have these two data sets, and joining tables only happens in two data sets at a time. Even if you have like, I have to combine all four of these tables, yeah, you still have to do them pairwise. And sometimes the order does matter. So you do have to pay attention to that, but we'll talk a little bit about that in a couple of minutes. All right, so we have our encounters MI data set, right? That's our encounters data set. Because I typed it first, it is the left data set. I want the encounters data set, like the 70 observations. I want that to stay fixed, right? So I'm going to do a left join because I'm doing a left join because I'm specifying encounters first and doing a left join. I can flip everything, but I would have to use a right join. So I'm going to use a left join, left underscore join, and that comes from tidyverse. And I'm going to tack on another data set. What is that data set? It's the patient's data set. Now I have to tell it, what are the columns I want it to match on? They're not the same. Not every program allows you to join tables with different column names. So R allows you to do that. Every single database system allows you to do that. Not every single programming or analytics system allows you to do that. But we can do that in R. How do we specify that? We say by equals. We put C because we're going to specify a list. And we can specify joining on multiple keys. That's an option as well. So maybe you're going to, sometimes you have multiple identifiers for something. In this particular case, that's not the case. That's not happening. But let's say we don't have the ID column in encounters. Well, then the identifier for a particular row probably is like patient and start time, because it's impossible for an encounter to happen, two encounters to happen at the exact same time, right? So maybe that's how that encounter, that table would be identified. But that's something you need to think about because maybe there is going to be a case where two encounters happen simultaneously. You never know. So how do we say I want the patient's column from the encounters data set? Well, we put in patients. And that's the name of the column. Oh, sorry, it's patient. And it comes first because the encounters data set is the left one. And then the right one is the patient's data set. What is the ID identifier, the patient identifier? It's called ID. Again, it's not the ID column in the encounters data set. It's called patient in our example. So now I'm going to run this. I'm going to save this to encounters underscore PT for encounters patient. And you'll see here, my encounters patient data set has 70 observations, right? We still have the same number of rows. Why? Because we did a left join and our left table has 70 rows. But now we have 39 columns. Why do we have more columns? Because all of the patient columns came in and it's tacked on to the right-hand side. So one thing you really need to keep track of when every time you do a join And this will hurt you if you don't do this. There's a function called nrow for number of rows. Every time you do a join, run this command to give you the number of rows, right? So I'm doing a left join. My final value has 70 rows. My encounters, I expect it to have the same number of rows, which is 70. And then if I look at my patients probably going to have more rows, but only the ones that matched was kept. So I like highly encourage you, almost like if I could mandate it, I would make you run this set of commands to visually check, because it's also really common if you don't specify, one, if your relational database isn't specified properly, or you did the wrong join in the wrong order or whatever, it's very possible you end up with 10 rows in one data set, 20 rows in another, and 1,000 rows as the outcome, right? Or like 100 rows as the outcome. It's very possible that can happen. And so you definitely want to check that. And also another thing is like, well, if I have 70 encounters and for some weird reason I did the wrong join and I end up with, 11 or like 1,000, I know like, hey, I did something wrong, right? And that's important because your data set's wrong. Whatever analysis you're going to do is going to be incorrect. So you want to check that. The other thing I want to show you is if you are going to visually check this, you might as well write code that will do the checking for you. And if that bit of the code doesn't meet your expectation, then you tell the code to stop running. So what is the thing that we want to care about? Well, I'm really checking to making sure that the encounters patient data set, the number of rows there is equal. So using 2 equals to the same number of rows as the encounters MI, right? Like I want those 2 rows to be exactly the same. So all this gave me was a true. It hasn't stopped the code yet if it's wrong. So the way we do that is we wrap the whole statement around a function called stop. If not. And now, if that statement is true, it'll just silently go past, like nothing's going to happen. But if that statement, for example, we expect this to be 100, if that statement is false, it's going to error out. And if you run this code like in the background, it's going to stop right there. And it's going to tell you this is not true. And so I highly suggest and recommend when you're doing analysis code, and especially if you're doing joins or anytime you're putting code to the screen and to visually check it, write the code that's doing the visual check for you, and then wrap that check into a stop if not statement. Where this thing has helped me before was at one point very common in data sets and health data sets, instead of leaving a value empty for missing, they put in 99 and that's like the missing value. So that's different from like, no, the person didn't answer and I know and I acknowledge the fact that it's not person didn't answer and it's missing, versus like me as a data entry person forgot to put it in. So what I've done at one point was I took my entire data set, replaced all 99s as missing value. And then when I went to go check like, hey, I expect like unique values for, I encoded 88s and 99s for my entire data set. And then when I got to the point where it's like, I only expect like 1 observation per patient. And then when I tabulated that, one of those was 2, and it's because there was 2 patients that had missing values. And I was like, impossible. And why was it? What happened was because like the patient IDs went from like 1 to 1,000 and there's 88s and 99s in that range. And like this stopped the code because I made an assumption and it broke. And that meant that actually my very first step when I loaded in data was incorrect. So that's how you can stop yourself. And anytime you're making an assumption of your data, like write the code to test it and then write the code to stop if that test is broken. Okay, so what we can do here, now that we have encounters patient, we have everything we need, right? So if we scroll to the right, we have birthday. We can convert that to a date timestamp. And if we look here, birth date is a date. That's good. And then from the encounter side, we have start date. So all we need to do is subtract those two values, and then we get time of age of encounter. And I realized I sort of screwed up my notes on this end. So I'm partially like doing this on the fly, but how do we make a calculation? We're running mutate, and then I'm saying, what am I saying? I'm saying start minus birth date, birth date. So I'm going to say age at encounter is equal to that. All right, that sort of got all screwy. The joys of live coding and not having your notes properly processed. But I have the code somewhere, and instead of just hunting for it like right now, you could go through the process of turning this into a date time. So maybe I can say YMD. So maybe this is a looper date thing. Hour, minute, second. Yeah, and I think birthday is just year, month, day. Hopefully this works. I guess it doesn't. I will look up that little bit on the next break, but you can do a calculation very similar to this. And get the age of time of event for their emergency visit. And just so you know, what you end up finding is like you'll get that age calculation if you like plot the histogram for it. You'll notice that it's very bimodal. There's a group of patients that come into the emergency room for a heart attack that's like under 25 years old. And then there's another one that comes in for a heart attack at around 55. And so like you see this bimodal distribution. And remember, like you can come in for a heart attack for like other reasons. And so why is there a distribution? Probably something you want to look into. And like just doing quick glances at this data, it was like maybe one is more like heavily on like drug addiction problems, and the other is like because of you're just getting older, and stuff like that. So that's what you can do with that little bit of combining tables. And that's only made possible by running this join command. So I want to talk about the next thing, and then during the next break, I'll go and figure out the little code for this. So at least it's like there for you. So this won't work for now. I'll go fix it. It's literally like in code base somewhere. But how do we translate all of this stuff to databases, right? Like you're almost never going to be given access to your hospital's data by CSVs. At least you shouldn't. And so chances are you're going to have to make a database connection. I do not have the ability to fire up a fully populated hospital database. So we're going to have to fake some part of it. In one of our data sets is a portion of the Cynthia data in a mock database for you that we can connect to. And the main thing I want to show you is how tidyverse works in relation to databases. So we're going to work on the same script because it's still on. Actually, we're not going to work on the same script. We are going to create a new script. And I am going to call this 03 databases. And then that sort of prompts me to like go fix the joins thing at the end. And I'm going to restart R just so we're in a clean slate. So if you're sort of behind, this clean slate wouldn't matter if you're behind or not. All right, cool. So we're going to load up tidyverse. And Oh, I know what's going on here. Ooh, this is interesting. So there's a package called RSQLite. So you can click on the little thing and install it. It's going to be much faster if you install this on Windows and Mac. And I understand why it's not installed, but that's other technical reasons going on in the background. But we're going to use the RSQLite database. SQLite is a database that's special in the sense that the database is completely self-contained in a file. So instead of just shipping around like 20 CSV files, I can give you 20 CSV files in one file, and that file is in a database. Okay, so before we even talk about databases, let's go through some example just with what we have. We can patients. So we'll load up the read_CSV. Sorry, it's under data, Cynthia, patients. So this is the patient's data set. Same thing that we've been working with this entire time. What's one thing that we can do with this data set? What if you can do all of the, sorry, and I'm also going to pass this into clean names from janitor. Actually, what do I want to do? What do I want to do? No, I'm not going to pass it through clean names. Sorry. We have our patient's data set. I do that because like this is not how it's set up in a database because I just blindly did that. So I might have to change that in the future. But we have our patient's data set. I showed you how we can filter data. We can use the filtering function, right? So let's do something. Let's do a fairly simple filtering. Let's say we only care about, I cared about like marital set. Like, let's say we just care about one specific subset of our patients. What is their marital status? So that we can do, use filter. There's a column called marital. And in this example, it's going to be all uppercase because I didn't pass it through clean names. And we're going to say marital is equal to capital M for this is a patient who is married. And I can do something like maybe I only want to get the ID column, the birthday column, birth date column, the death date column, and the marital status, right? So I can filter my data set just like we've been used to doing. And I can even do something like, hey, just give me the head of 5, like just give me the first 5 rows, right? So you can use this head function to sort of get the first couple of rows of something. The more built-in way, I believe, is slice. But head, this should work. I believe this works. I think this works. If my notes are correct, this works. So that's one way we can filter our data set, right? Nothing too fancy there. Let's see what this process looks like if we were to make a database connection. So in our SQLite, if we run that library, we have a function called dbconnect. Stands for database connect. The code is a little bit weird, but you should really only need to do this once. We're going to make a SQLite connection. So don't forget the round brackets. And then we pass in, just like read CSV, we pass it the actual SQLite database file. So in the data folder, there's a file called cynthia.sqlite, and this is the database that has some of the tables from the full Cynthia data set. We're going to save that to a thing called connection. So CON for connection. And now we've made a connection to a database. So this is going to vary depending on however database system you have set up, right? So if you've worked with Postgres, you might have to have that set up differently, et cetera, et cetera. There is a library called redcap-r. If you're trying to make a redcap connection, you can connect to it from R. Depending on the actual backend for Epic, you might end up being able to make a connection straight to that part of the database. I know that Odyssey and OMOP has their own common data model. A lot of people will have the underlying thing under Postgres. And so you have to work and figure out how to make the actual database connection. So this line is going to be really specific because we're working with SQLite. It may or may not have more lines to make the connection, but the main takeaway is you need a database connection. And so I'm going to hand wave there and say, like, that's going to be very difficult to make it super generic for everyone, but that's how you make a database connection. Now that we have a database connection, and this part should carry over once you have the connection, there's a function called db list tables. And if you give it the connection object, it gives you all of the separate tables in the database, right? So in here, I only have 2 of the data sets loaded in. Originally, I had all of it, but I couldn't post it on GitHub because the file was too big. So I just reduced it down to 2, at least for now. We'll see how that works out in the future, if I can compress it a little bit more. Okay, so we have individual tables. What is the equivalent of read CSV? Like I want that particular table of values. Well, within tidyverse, there is a function called TBL for tibble, or give me a table. From this particular database connection, give me the patient's table. And I'm going to save this into a value called patients underscore DB. And I would have gotten the patient's table from the database. You'll notice one thing. If I run it, I get the actual values. This is the actual values from the patient's database. If you look on the right-hand side, it's not actually saved on your computer. What it did was it queried the database and then gave you the results back. So this stuff isn't actually loaded on your computer. So sort of the nice thing with dplyr or tidyverse, if you're doing these simple filtering commands, like it only works for like a smaller subset, but if your thing is like doing joins, doing filters, I believe like mutate to some extent will work as well. All you need to do is take that connection to a table, so like that database table, and you'll notice if I scroll all the way up and I copy the exact same code, like completely unchanged from the local CSV file, and I run it, you'll see that I get the exact same results, but instead of running it from a CSV file, this is literally querying data from the database. So if you can get your hands on like a mock example of your database that's small, you can run your code on your local computer, make sure everything runs. And then once that runs, you can then say like, okay, now I'm going to make the real connection to the database. That's going to be the actual report or the actual set of results that I need, and then run it that way. The other benefit of that is you can work on code that's a smaller subset of your data, and then like say like, hey, I ran this, and give it to like, hey, tell the analyst who actually knows how to run the database connection and be like, can you run this batch on your database connection? And so if what you need is some filter, you can pull down stuff from your database and then work on a subset that you need. So you don't always have to work with the full, million rows. If you only know right away, you need a subset of your patient population. So maybe you can filter on ICD-10 codes. These are all of the patients with these. Maybe you'll want to do joins to look at the encounters and the patients, and only filter on heart attacks. You can do that on the live database and then filter it down to the point of only the things you need. And then you can run all of the stuff that I talked about in the first hour about like running calculations, calculating dates, et cetera, et cetera. But I believe a lot of that also works in the regular database connection. If you know a little bit about SQL, and I'm not going to try to teach you SQL other than like, hey, if you just know I want that data from that table, like all of it, just give it to me. I'll give you some like copy and paste examples. Like if you don't want to write the filtering statement in raw SQL, you don't have to. You really only need to say like, I want everything, give it to me. And then it'll get loaded into R and then maybe save it out to a CSV. I don't recommend that depending on HIPAA things, like make sure this is all saved into like a proper like encrypted location and not just like on your desktop that you can email. Like don't do that. But if you need to make, if you already have a learning path learning R, like instead of tacking on another learning path for SQL, how can we write simple SQL statements that give us everything and then use the techniques from regular R that I'm showing you to filter that stuff down. So there is a function called db get query, and it stands for database get a query. We pass in the database connection object. So everything's always going to look with like this connection object. And then in single or double quotes, it doesn't matter as long as you begin and end with the same. But from what I've seen, everyone uses single quotes because depending on your database, they use double quotes for relating to things. So it's better to use single quotes. And then all we need to do, if we want to get everything from the patient's data set, we say select everything from the patient's table. If we run that, it's going to make that query to the database and then return this back to you as an R data frame. If we don't want all of it because it's like a million rows, we can say limit 5, and that's going to say like essentially the equivalent of head 5. So I can save this to like PT DB 5, right? And now I have a regular R data frame and everything that I've taught and covered applies, right? So if that's all you need is like, I just want everything from this data set, just here's the table, here's the thing, here's the code, here's the SQL to do it. You're gonna select all of your columns and you can specify individual columns if you want to do the filtering in the like in the middle. And then you can limit, which is head of 5. So a little bit more, if we want to replicate this little batch of code that we just did. So the limit 5 is this head 5. So we want to select just this set of columns. So the way we do that, instead of star for select all we need to do is say ID and then comma separate ID, birth date, death date, marital, from the patient's data set, limit 5. And you can see we also did a subset on the columns, and that's all we need to do from there. So instead of star, we put in comma delineated sequence of values. And then if we want to see like do this filter step after patients, we say where marital is equal to in double quotes M. And now we filtered where our marital status is M. And so that's roughly how you can write SQL code and stuff like that. The last thing I want to show you is, let's take this data set that we just queried. Let's say like, hey, this is the code that's making the direct connection to the database. I do want to show you, you can pass that entire statement into a function called show query. and it will give you the SQL statement. So you can see, like, if I literally copy paste this into that like quoted statement, it will give me the same set of values, right? Like this statement from tidyverse is literally writing the SQL for you. And so what you can do is literally copy this. You can maybe put this in an email, depending, like, you don't like say like patient equals like MRN number, but you can send this off to someone else and be like, hey, this is the table, the SQL statement for the data. Can you run this on your end? And that's something that a lot of people end up doing with Odyssey and OMOP or any other common data model. They run the SQL commands on their own hospital system because they have access to it. They then share the SQL code. All of the other hospital systems that have the same common data model, all they need to do is run that SQL script. And now you have a really convenient way to do like a multi-site meta-analysis or a multi-site analysis across all your patients, because that's assuming that your underlying database is set up the same. And then once that's the same, hopefully the SQL code that runs on your computer runs on theirs. And so that's how a lot of that stuff ends up working together. All right, so I'm going to move on to the next topic for today. And this will be the last topic for today, which is on functions and how to write functions and use functions, et cetera, et cetera. So we'll take another 5-minute break. So come back at 57 past the hour. And we'll talk about functions. And if you have any questions, just let me know. Okay, so let's get started on the next bit, which is going to cover functions. And I am sort of at the point where like the notes that I have published is I have the actual set of materials in another file, but we'll go through the function stuff that I have published right now on the website. And then if we have more time, I'll sort of go through what we can, I'll sort of open up my actual raw code notes, and then we can go through that stuff, assuming we have some extra time. So I'm going to talk about functions. We're going to do the same thing. I'm going to create a new file, go to session, restart R, just so we are all starting from a nice clean working environment. And just like we're used to, I am going to load up the tidyverse set of functions. And we're going to start off with a short review exercise. So if you remember from the R part 1 section, if we load up read CSV and we look at the TB_long data set, this is a data set that is coming from the WHO, and for a given country year and gender and age group, there's a frequency count for tuberculosis cases. So let's take 1 minute to tidy up that data set. And what I mean by tidy, if we look at this data set again, I want this data set in such a format where I have a country column, a year column, a gender or sex column, an age group column, and then a count column, right? And just as a small review, the reason for this is if we look at this value, for example, 52, that cell it has 2 bits of information in it. It has a gender bit of information and an age group. Because if we scroll over to the right, there's going to be the same thing that is the female equivalent in this data set. And so right now, there's no good way to say, what are the total cases in Puerto Rico in the year 2005 for age group 0 to 14? We don't really have a way to filter our data set that way. And that's because gender and age groups all combine into one thing. Yeah, we can use some of the techniques I showed you to filter and slice and then just pull out the numbers and then do the sum, but it's a little clunky. And we definitely can't say like, we can't pick on a column. So if we were to plot results, we can't say like, I want the total sum. I can't group by age group. I can't group by gender to calculate frequencies and make a plot out of it. And all ties back into like the ggplot stuff that we covered in part 1. So that's the problem with this data set. So I want you to take about 1 minute to tidy up this data set. And let me present the code. And this is how you load up the data set if you are following along. All right, so let's go over the actual code example for this. If you are following along and you didn't go through the exercise, type what I'm typing because we're going to use this data set for the functions example. The thing I wanted you to recognize here is this is a pivot _ longer operation that comes from tidyverse. And we want to pivot this data set such that we have to select the columns that begin with male to female. There's different ways we can do that slicing. In part one, the actual code that was like the last thing I showed you was using the starts with selector. And I'm saying if it starts with M or starts with F, I want you to pivot those columns down. So now we have this data set that's country, year, name, value, part of the way there in our tidy data set example. So now the next thing I want to do is take this name column and split it down the first character. So I get the first character is going to be gender and the rest of the values is going to be age group. So I'm going to take that data set and I'm going to pass it into a value, pass it into a function called separate. This is going to, what is the column I want to split? It's going to be the name column. I'm going to split that column into two columns. One is going to be called sex, and the other is going to be called age underscore group. And the way I'm going to separate it is going to be based off of the first character. You can do that separation. There's many ways you can specify this. We talked about different heuristics. So maybe, you don't always have to split by the first character. If you're curating your own data sets, use underscores and dashes, like use them strategically in such a way where when you get to this part, you can split your data set easier. So it's okay if the way you curated your data set was in one format, just leave yourself breadcrumbs so you can process your data. And honestly, like underscores and dashes and some combination of those is probably your best bet. All right, so if we look at this data set, and if we, I'm not going to go through the Hadley, the tidy data paper by Hadley Wickham, but if we looked at the actual values from the tidy data paper, the age group column actually was printed prettier, right? It said like the age group was 0-14 and then 15-24. And then instead of you, it would be unknown, or I'm going to say like, let's just treat it as unknown. So let's break down the problem, right? Like we are now in the process of one, we're going to be working with strings and we're going to try to recode or relabel this column of values. And there's going to be many different ways of doing it. I'm using this as the example to teach about functions. So before we get into functions, let's just break down the problem into what we want, right? So before you even think about code and all of that, here's your column. So let's write some code to figure out what are all the unique values in here. So I showed you tb_tidy. There is a function called distinct, like that I showed you in the very first hour. And if we give distinct a column name, it'll give us all of the distinct values. So here are all of the values for the age group column. And I want to make it pretty, right? So like given any random one of these values, come up with a set of heuristics to process that value. So let's start like, so one thing we can do right off the bat is like, if the value is equal to the character u, then replace it or return a value that's like unknown, like all spelled out, right? So that's going to be a roughly easy example because it stands out so much. What about for everything else? What's a heuristic that we can use for all of the other age group like values? There's many different ways you can approach this. This is when people talk about data science sort of like being an art or programming being an art. This is sort of why, because there's so many different ways you can process this, come up with different heuristics. Yeah, some is going to be a little bit more efficient than others, but as long as your answer is correct, then you should be okay. And that's actually more important, is making sure your answer is correct, right? So remember in the first hour, when we're looking at hospital readmittance, just filtering off of emergency visits was not the correct way to do it. We actually had to filter off of other like key terms. So come up with a bunch of heuristics, but then, you know, it's also good practice to like try to run the same calculation in different approaches to make sure like things are being calculated properly. So let's take this 014. How would I turn this 014? First, I need to identify that it's 014. And then how would I pull out the part so I can write 0-14? So let's break down this problem into specific steps. First, I told you about if the character is just the letter U, return unknown. So let's just write a function that does that, right? So I'm going to create a function. It's going to have a name. The name of the function we're going to write is called clean age group. In general, make your functions meaningful. And then if it's a function that is doing something, start the function name off with the verb that it's trying to do. So I'm going to call this clean, but you can also call it recode. You might also call it like whatever. Just start it off with a verb, and it'll sort of help with the like how your code reads to other people. I'm going to create a function. So the key term is going to be function with a set of round brackets. So we call functions with round brackets. We create them with round brackets. We're going to pass in a temporary variable. So this function, its input is going to be something. That thing, we're going to give it a name called age group as a string. And then that's how we're going to be able to call this function. We pass in some value. That value is going to be referred to internally as a variable called age group string. The way we create the body of the function is with a set of curly brackets. And now everything between that outer set of curly brackets is what this function will do, right? So I can write a function that squares a number or adds 2 to a number. I would end up putting like this thing plus 2, and that's how I would write this function. So this function is going to be a little bit more complex, as like it's fairly complex as far as like very first time function examples go, but I'm hoping that the complexity is worth it because it means something. So let's say I only want to do with that U case, right? So first thing we want to do is to check if that value is equal to U. So let's write that statement. If and in round brackets, that input variable is equal to the character U, we're going to use another set of round brackets, return like unknown. And so that's our function. Every time we go and modify this function, we have to run it again, so it doesn't automatically update. You'll notice on the top right-hand corner, you'll now have a function that you just created. And the way we use it is just like using all the functions that we have been calling from tidyverse. If I pass it in, oops, it's return. So because I made that change, I have to rerun the function again to like load it. If I give it the input of U, it returns unknown. Right, so we dealt with one part of the problem. If I give it some value U, return unknown. It doesn't know how to deal with anything else because we didn't write about, we didn't write about those cases. So if I say 014, it's just going to give us nothing because we didn't do anything with all of those other cases, right? All it knows is if it's a U, it's not even if it starts with the U. It's like, if it's just the character U, return me that value. So remember when I said, like, if you're going to visually check something, write the code to visually check it. So I expect this to come back as unknown. It's going to be true. So now I'm going to wrap this around stop if not. Because I'm going to keep adding to this function. At least I know if I screw something up or add something incorrectly, I I didn't break this example. So I don't have to constantly go and recheck all of the things I'm checking. I can just say like, run this whole batch of things. If any of them return false, it's gonna crash. And then I'll know which is the visual check I was making that didn't come out to be true. Okay, so that's the super simple case. What about everything else? Right now, I just said, if the value, the complete value is equal to you, I can then, one way I can do this is I can say, if the value is 0 to 14, return 0-14. If the value is 1524, return 15-24. If the value is 2534, return 25-34. I can do that. You can also choose to do that. If you end up with 50 groups, probably something you want to rethink about your approach, right? So here we have 8 groups. Fine. If I'm like super hard pressed to get this out within the next 5 minutes and I am very new to writing functions and et cetera, totally fine. Getting the work done is better than getting the work not done, right? It's infinitely better. Or it's like not a number better. But there's other ways, right? So we can come up with a couple of heuristics. So let's say we want to come up with a heuristic that is, if the input value begins with 0, then do something with it, right? And that gives us some benefit that if we collapse these age groups together, we can get something like 0 to 24, not just 0-14. And we don't have to worry about 0 to 9 because our data doesn't have it, right? So if the heuristic was, if the starting input is a 0, then do other stuff with it. What is the other stuff? Well, I want you to pull out the first character, which is a 0, then put in a dash, and then take everything else and put it as its and then tack on everything else that's left over. So instead of just writing the function, you can break down your example into its own parts. You don't have to test everything as a function. So remember when we loaded up tidyverse and I said like str_ is like all the things that you can do with like string operators. So if we say str_, there's actually one that says starts. So if we say, if my example input is 0-14, and if it starts with the value 0, it will return true. So cool, this is a great way for me to detect if it begins with 0, do other stuff. And I have the scaffolding over here to say, if this statement is true, go do other stuff. Okay, cool. So I have that bit, so I can detect whether or not it begins with a 0. How do I go and cut up the little bits, right? Because I want to take out the first column, make that the first character, then manually put in a dash, and then everything else. So like I said, no, it's almost like none of those basic operations are going to be like brand new. You don't have to work with it. So what is the thing? We want to subset our data frame. We want to subset our string. So if we look at str_, there's actually a function called sub. And what that does is if we give it some kind of input, for example, 0-14, we can say, start from the first character, end at the first character, and it gives us the 0, right? So we can now pull out the first column. So that's one thing that we need. The other thing that we need is, once you pluck out the first one, I want you to take everything else and I want you to capture that. So how do we do that bit? So now we can say, start from the second one. If you look at the documentation, if we put in a negative number, it just goes to the end, right? So now we have all the little bits and pieces that we need. We know the code to write, to check for the first character beginning with 0. And then I can pluck out the first character I can manually put in a dash. That part is roughly okay. And then I can pluck out and do the rest of it. So that's all of the inputs that we need, like in terms of like how we're going to handle if the string starts with a 0. So now let's go back to the example code up here and add another statement. So the way if statements work, we can keep putting in if statements, but R is going to keep checking every single one, right? So this is another way we can, if you know a little bit more about programming, it's called short circuiting. If it hits the first case that's true, then skip the rest, right? And so it doesn't have to make these every single calculation. This comes into play because sometimes these calculations can be really expensive, like takes a bunch of time. This saves you from running all those calculations that don't matter, right? Because it's going to have to do this conditional check, even if it returns false. So the way we can say like run through these conditions and stop at the first one that returns true is we say else if, then the condition followed by the brackets for that statement being true. And that will make it so that once it hits the first one that's true, it skips all of the other ones. So we're going to keep tacking on else if statements. So we have the little bit for 014. So let's write in that part of the code. All right, so what was the first thing? Well, the input was if the string starts with, so what is the string? This thing that we're putting in as input. If it starts with a 0, it's going to return true or false. And then once we have that, we have all the little bits that I created, right? So I'm going to say, I'm going to create a variable called age cat. And then how do we manually tack together that sequence of letters and characters, et cetera, et cetera. So one way, I'm going to show you two ways. I'm going to write it like the quote unquote, depending on where you're coming from, like the easier way. And then we'll rewrite the function again, and then see how it can look in two different formats. There is a function called paste 0. And all it's doing is anytime you give it a set of strings, so let's test it out here, paste 0, if I give it like hello, and then I say, because this is also streaming on Twitch, if I say something like hello, Yuka, and stream, because there's a 0, it's just going to tack in all of those characters one after the other, right? And so we can use this to our advantage because we can say pluck out the 0, tack in a dash, tack in everything else. So we can do that. So what were those parts? Well, it's all this substring stuff. So I'm going to say str_sub. We're going to subset this. We're going to say start from 1, end at 1. And so that gives us the first character. So we're building up this example. Let's just make sure that this code works. So if that's the case, we're just going to say return the age category variable that we've been working on. So let's run this. I'm going to run through and make sure that I didn't break my first example. So that's great. If I pass in this next example, 014, right now it's only returning 0 because all it did was pluck out the 0. So let's go back and first, let's go back, write the condition. What we want is 0-14. Sorry, if it's 014, we want the answer to be 0-14. So right now, the way the code is written is this is just false because it's not true. It's not working, right? And if we run the thing, it's just returning 0. So let's modify this line here to account for everything else. You have to be very careful about how the round brackets are working. But we have paste 0. The first thing is taking out that substring. I'm going to hit comma. The next thing I wanted to write is the dash. And then the last thing I want to write, well, it's going to be that substring again. But instead of starting from 1, I'm going to say start from the 0 and then go all the way to the end. And so we've created that string. I'm going to rerun the function to load it up again. And now if I just run that line, you see that I get 0.14. If I run the conditional check, you see it passes. And so now I'm done. And then I can run the first one to make sure I didn't screw that one up either. Right. And then now we can just go and build on this example for all of the other scenarios. And then every time we have one of those examples, if we're going to visually spot check it, we write the condition down here to make sure we didn't screw something up, right? All right, so let's go back to this example. We have begins with 0, starts with you. What's some heuristic that we can use for everything else? You can come up with anything. What I ended up doing, just so I can show you different techniques of working with this. The next one was else if, let's say that the input, so I'm saying like if this input is equal to 65, well, then we can say return 65 plus, right? So that's a pretty simple example. We can use that as well, right? It seems like unique enough. That's totally fine to work with. So I'll run this. I'm going to copy the test case example and say, if it's 65, I expect this to be 65 plus. If I run it, it passes. I can convince myself again, if I put in 65, it returns 65 plus. All right, we're almost there. Let's look at the input data again. Everything else follows a pattern that I identified as, if there are 4 numbers in there or 4 characters in there, then take out the first 2, put a dash, and then take out the next 2. So I want to show you how we can count how long something is, or count how long a string is. So that bit of the code is going to look like str underscore. And if we look at string, there's length. And now if I put something like 1524 or 1534, it's going to say 4. It's because it's 4 characters long. So we can use that to our advantage in our code. And so I'm going to say else if str length of our string, if that's equal to 4, go do stuff. What is the stuff we're going to do? Well, we're going to roughly do something very similar to that pasting thing that we did before, except instead of starting from 1 and ending at 1, we're starting from 1, ending at 2, putting the dash, then starting at the 3rd character, and then going to the end, or I can put in a 4 if I want to. So we can run this. We can see that all of my previous code is not broken. And now if I put in any like 4-digit number or letter or whatever, I'm going to expect that to be like 36-45. And yes, that's true. But let's actually do it with some of the variable values I care about. So the values I care about is going to read, what is values? 45 to 54, right? That's one of the age groups. So 45, 54, I'm going to expect. So now you'll notice sometimes, yes, your test is going to go wrong, but at least it's stopping you. So this is supposed to return 45-54, and that works. All right, cool. So that's our function, right? So now we can essentially go and apply this to our data set if we want to. Before we do that, I'm going to copy this function And I'm going to create a, I showed you a different way we can work with this string paste thing, just to help like clean this up, because again, like there's a lot of rows in here. So one technique you can do is for these things that have multiple parts, you can give it like a temporary variable that's like, hey, part 1 is that part of the string. Part 1 is that part of string. Part 2 is this other part of the string. And then all I'm doing is putting in part 1, part 2, right? So that 1 makes your code not as like wide, and so you don't have to read as much. And 2, your brain is going to be like, okay, part 1 is what? Okay, it's some substring. Okay, I have a P1 and P2, and I'm going to tack them all together. So you can reduce the amount of things you have to keep in your mind if you write your code in such a way where it's like not all one giant statement. Like break it up into pieces. One, it's less wide, so one, it's easier to teach out of because it all fits on a screen. And that's usually also a good visual cue. Like if it's too wide, like you probably are doing too many things in one statement. The other thing you can do, and so let's run this function again, and then all of those checks, make sure like it worked, right? Because I made a change to this function, and you'll notice that like, okay, everything that I worked on didn't error out. So that part didn't change any of my expected results. All right, so what's another technique we can use instead of using paste 0? There's this glue function, glue library, and I'll do it for the example at the bottom. We can save yeah, so let's do this for the example at the bottom. So I'm going to still do the P1 breakdowns because that we still have to make those calculations. There's no way we can get around that, right? So I'm going to say part 1, part 2 is going to be those substrings. And then how am I going to use this glue function? Well, instead of paste 0, there's this function called glue within the glue library. And in here, we can put in double quotes, like we can manually construct the string. And if there's a variable in the R world that we want to bring in, we can put it around curly brackets. So we can say P1, close open curly bracket, a dash, and P2. This is how we can use the glue function to do the same exact thing as paste. And some people like this statement because it's much more clear, like, okay, I'm taking the input for P1, then I'm literally putting a dash and then whatever input for P2. And you don't have to worry about like, is paste 0, like putting spaces in there or commas in there because there's other parameters that's going on. This makes it really explicit, like, hey, this is what I want. It's like the value for P1, a dash without any spaces, and then the value for P2. So I made a change to this function. Let's run that whole thing again, and then run all of my test cases to make sure I didn't break anything, and I didn't. So now we have our function. Why did we go through this whole process for our function? Well, that's because we needed that function. And in our TB tidy data set, we wanted that function to work on this column, right? And you can replace that whole function creation for whatever process you need for processing a column, right? So, you know, maybe it's a thing like, this sounds like this sounds easy, but it's actually it's more complex than it sounds like. But like if your thing was like, identify whether or not this is a telephone number that is valid in the United States and Canada, and then convert it into a standardized format, you can write a function to do that. It takes in whatever the user put in. And the first thing you got to make sure is like, is this a valid telephone number in the United States or Canada? And I say that because the country code is 1, right? So there's different, like the amount of code or the checking thing to make sure that it's a valid telephone number. Like that's one of the things you look up and it's like, what is the pattern for a properly formatted US telephone number? and then you can process however you need, right? So substitute that with whatever you need. In the one thing, I guess, that you can, so this column can also be like, here's the raw text for a clinical note, right? And you're trying to identify like what is like this patient's history, right? That is something that you can use with a combination of all these string underscore methods to pull out bits. It's a lot more complicated because you have to identify those patterns, but the raw pieces to make that are all there for you. And you have to figure out how to patch them together. So in this case, all we want is, I have this column called age group. I want to take that function that we just wrote and literally apply it to each one of these age groups. So how do we do that? I'm going to show you, the reason why I'm going through this. The reason why I'm going through all of like this explanation is like, I actually haven't shown you any part of the code that can do that for us, right? So if you try to use everything I've taught so far in like, oh yeah, I can now say like, treat it as like the mutate or filter function that we've been using and pass that function in there. No, that's not how that works. So I am going to try to see if this copies. And if it does, it does. But hopefully that works for the people on the Zoom side of things. So let's say I want to use this function, right? So I have TB, tidy, right? Like, let's say I want to use the clean age group function and put in age underscore group. It's not going to work, right? That's not how you use custom functions to work on your data. Or maybe you're going to say like, hey, wait, no, I'm trying to modify a column so we can use the mutate function. And I'm going to say age cat is equal to this, right? Because that's roughly how mutate works. That's not correct either. And you'll notice that right away, like, I know this function works, it's not doing it right, or it threw me an error, right? So that's not how that works either. So the reason why we put so much time and effort into tidy data principles is because you need to be able to point to columns for analysis, but you also need to be able to point to columns to process and clean them in custom ways, right? If I can't point to a column, I can't write a function to process it. And so the first step is to get your data set into a way where you can point to a column. If you need multiple columns, then you have a way where you can point to multiple columns. And that combination of column values is what your function takes. And I'll talk more about that tomorrow. There's going to be like a small homework assignment, but that's what you need to have your data set in. And if that means doing pivot wider to temporarily have your data in a format that's conducive for that, then that's what you do. You know how to use pivot longer and pivot wider, and you can use that any one of those formats for what you need to process your data. And the reason why I talk about that is there is a library called PUR or Pure R. It's PU with 3 R's. And the PUR library has a set of functions that say, you have a function, you give me an infinite number of sequences, and I know how to handle each one of those sequences one at a time. The reason why it got screwed up here is because it tried to handle all of those values all in one big block instead of one at a time. So we have a function, we know it works for individual one at a time cases. That's why I wrote all of those test cases. It's because I proved to myself, if it's not working on my data, it doesn't seem like it's a problem with my function. It's a problem with how I'm using the function. So in PUR, there's a whole family of functions that begin with map. We can use regular map, but the outcome that we care about is a character. So there's map underscore CHR, there's map underscore like logical or number or whatever. This is a function that takes in some input, but its output is a character. And so there's a map underscore character, so we get a character vector back. And the way we can use this is we can say TB underscore tidy. We can pull out, so I'm going to use the $ notation to pull out a column. This is the same thing as running the pull function in dplyr. So I'm going to say like, give me the age group values, right? So if I just run that bit, you can see like, these are all of the inputs for the age group. And then I'm going to say one at a time, run the clean age group function. And you can see now I'm getting the properly formatted code, properly formatted string output, right? 0 to 14, 15-24, and that's not 1-524, right? That was the problem we were having. And so now we have our one, a custom function that we wrote, and two, we can pass in a whole column of values, and then that function knows how to operate on that sequence of values one at a time. And that's because of the mapping function. And then it's giving it back to us as a character because it's a map character. So that's fantastic. We have all of the values that we need to recode. Now all we need to do is actually put that back into our raw data, right? And so how do we do that? Well, now we can go back to the tidyverse stuff that we covered. So it's TB tidy, mutate, right? So we're actually modifying column. We're going to make a new column instead of overriding the original one. So I could say age underscore cat, and it's going to be equal to this map statement. I don't need to specify the data set anymore because it's under this mutating function. And now you'll see for each one of these age group columns, it passed in and used our totally custom function, processed it one at a time correctly, and created a new column with it. And I don't have to worry too much about checking the values in here because I wrote test statements for everything. And so all I need to do here is like TB underscore tidy, save that to a value. And now I have this TB tidy data set, right? And this is great because now when I go and plot, I have like a nicely formatted column that I can use for plotting, right? So what's something that I can do here off the top of my head? So I can load up ggplot2. And now I can say TB underscore tidy. I can say group by year and age cat. Right now I can get counts for each year and age group, like what is the sorry, it's not count, it's sum. Sum of I really hope I'm doing this correctly. Is that right? That's not right. Live coding is interesting. How do I get the sum of this? I need to think about this. Oh, it's sum of value, right? And it's sum with na.rm equals true. Okay, so I can now take like group by year and category and then sum up the values in the value column. And because there's missing values in there, I have to tell R like drop the missing values. And so now I can see like for every given year and age group, like how many TB cases there were, right? And I can then go and plot this. If I use the age cat as a variable, I now get like a nicer, prettier format of the thing versus like 2534. And it's like, oh yeah, that means age group, right? So now like what my figure is going to be plotting makes more sense in my head. So if I take this, let's see, year age count. I don't know if this is a good idea. Let's not group by year. Actually, we do need to group by year. Yeah, what's a good figure for this? What is a good figure for this? Okay, I know what we can do. So we can say ggplot, we're gonna make a bar graph, right? So we're gonna say, take that data set that we just passed in. I'm gonna use the age cat value as the X. The Y value is going to be the value for sum, and I'm going to add geom_bar. And then remember the layering function from ggplot, because I already did the calculation, I have to put in stat equals identity. And then here I get the values all there, but I still haven't used the year parameter. So I can say facet underscore wrap the year column. And for some reason, I guess it's only in the year 2000. So, but yeah, if I had more years, I would get a totally separate plot. But the main takeaway here is you can see here my x-axis is properly labeled, and that's because it's labeled correctly in the actual data set. For some weird reason, I always thought that that data set had more years than just the year 2000. So that's sort of where that exercise sort of went awry. But that's how we can write custom functions and then apply them to our data. And that means that you almost have no reason to not have the metadata for your data set travel with your data, right? Just have a column that is information about each row, or have them as two separate tables, put it into a SQLite file, and then now you have one thing. So everything is always traveling together. And so that's sort of like the main set of takeaways, like from today. Okay, so that's pretty much everything I wanted to cover for today, actually. One thing I want you to do, and because I don't want to sort of like publish this part for the world to see, because I might accidentally show an API key. What you can do is go to, if you Google US Census API key, and I know this looks super suspect. If you give in an organization name and an email address, you will be given an API key to query the US Census. So not everyone here is primarily focused on stuff around the United States, but I need to sort of show another like use case. So for homework for tomorrow, go to this site, request an API key. You will get the API key in your email, and I will show you how you can deal with it tomorrow. But the main point is you have that key, and this is the thing I didn't want to sort of just show on the internet. Because tomorrow what we're going to do is we're going to take essentially like this example of writing functions and applying them to data. We're also going to see how we can do this by downloading data from the internet without having to go to the website. specifically pulling down census and how to use census data, because that plays a big role with a lot of health data sets. You want to know, you want to make like age adjusted calculations for things. How do you know how age adjustment or population adjustment all happen? You have to know what the population is. Where do you get population data? You get it from the US Census or whatever census is in your country. And then once you have that data, you can then do like, you know, population adjusted deaths or something. So that's the example we'll start off with tomorrow. That's going to essentially cover a lot of, or review a lot of stuff we did today. And then also for tomorrow, what's on the docket is more of the machine learning stuff. So we'll cover survival analysis, and then we'll go back and review logistic regression and how and what the difference between an inferential model is and a machine learning model. And thinking about, just because the model ran, thinking about ways to make sure that this is a good model and trying to figure out like what are problems that can happen with our data set that we won't know about because none of the code will have an error. So how do we go about and figure out if model predictions are like good to be employed, like put into production? All right, so that's the plan for today. That's the homework for tonight, and that's the plan for tomorrow. And then sometime between now and tomorrow, like the website will go offline while I just copy and paste and update the stuff that's missing from today. One more thing before everyone leaves. If you do plan on, and I'll send this out as an email immediately after, if you do plan on coming back or coming here in person at VT, like in the space I'm in now, please do respond to the email. Just so like, because of all the random ways this is all set up for recording and everything, if no one expects to come here tomorrow, I can do my recording and all of that stuff on my desktop at home. So I'll send an email out for that. And with that, I will give you back 10 minutes of your day. And I'll hang around if there's like questions from the internet and in person.